Welcome to Lecture 3.2 on Quadratic Equations, Functions, Zeros, and Models in College Algebra. Today's picture is actually from Condom, France. You heard that right, Condom. And this is me amidst the Musketeers. We always hear the Three Musketeers, but evidently there are four. And this is on a hike in the south of France. Great hike. It's from Le Puy to Saint-Jean-Pied-de-Port. Excellent food. Accommodations are cheap for hikers, and a great adventure. Takes about maybe probably about 4 weeks. And a great way to experience France and the people, and to meet people from all over the world. This is part of the Camino Santiago. You can Google that if you're interested. Today's brief pause is a question for you to ponder. What are the things you like to do but haven't been doing? When I'm recording this video, it is 2020, and we're really in the middle of the COVID-19 pandemic. So right now for students, we think that there's many things that have been taken from us, and there are. But what are the things that you like to do that maybe you haven't been doing anyway, but you could do? Being outside, being in a park, etc. And I think it's important for us to kind of think through these things and to reflect on them, especially as Americans. I think in other parts of the world, we see both sides of it, but in other parts of the world, there's a better balance between, in my opinion, there's a better balance between life and work. One of the best things I ever did was work in Germany for a couple of years, because this really enabled me to hold a mirror up to myself and realize that I had put work in front of everything. And it was very alien to me that when I was signing my contract on the first day, that part of my contract said that I had 30 days of vacation, which is 6 weeks, and that I was required to take every single day of that vacation, and I was required to take 20 of those days at the same time. And everything about that was alien. The amount of vacation I had starting as an employee, the fact that I was required to take every single day, every single year, and that I also had to leave the office for a month. And it was just a different way of thinking about vacation. In America, we think of vacation as a benefit, a perk that the company gives you as a bonus. And in other places, vacation is thought of as healthcare, as mental health care, that just like in a sport, if you're going to stay on top of your game, you need an off season. You need a recovery time. And so that really kind of shifted my thinking in a lot of ways. So I challenge you to think about the things that you do, that you like to do, that you're not doing. And especially if you are listening in 2020, things that it's more important now when we're in this kind of social distancing environment to do those things that feed our spirit, feed our soul, feed our mind, and our body. Things that matter most must never be at the mercy of things that matter least. Goethe, another great German thought. And it's echoed in Covey's 7 Habits of Highly Successful People, that you always put the things that matter most in first place. And many times we don't do that. And I know that this is a constant struggle, I think, for most of us throughout our lives, to really step back from doing shit. And think about what is really important for me to be doing, or what do I want to be doing. And then a quote from Lord of the Rings: all we have to decide is what to do with the time that is given us. You're in school right now, and you're making decisions right now about the courses you're taking and the discipline you're heading to. Those are pretty big decisions. And while it doesn't lock you into a career or etc., it certainly heads you in a certain direction. So being really mindful about the things that you like to do, the kind of life that you want to lead, We spend a lot of time at work and thinking about the environment I want to work in, maybe as important as what kind of job do I want, what discipline do I want. So I really encourage you to break or pause a bit and to think about this. In today's lecture, 3.2, we're going to find zeros of quadratic function. Remember, zeros are where it crosses the x-axis. We're going to solve quadratic equations by using the principle of zero products. We're also going to solve them by using the principle of square roots, and also by completing the square, and by using the quadratic formula. So there's a number of ways that we're going to solve quadratics. We are also going to solve equations that are, we're going to solve equations that are called reducible to quadratic. They look like they're quadratic, but they're not, but we can reduce them to a quadratic. And then we're going to solve an applied problem using a quadratic equation. So a quadratic equation is an equation that can be written in the form ax squared plus bx plus c equals 0, where a, b, and c are real numbers and a cannot equal 0. A quadratic equation written in this form is said to be in standard form. Okay, this is pretty important that you remember this, that ax squared plus bx plus c equals 0 is the standard form, because we're going to use the values of a, b, and c in some of our calculations, actually in all of our calculations. A quadratic function f is a function that can be written in the form of f of x equals ax squared plus bx plus c. So this is just notation. Okay, so we have a quadratic function. It's in the standard form. The zeros of a quadratic function, f of x equals ax squared plus bx plus c, are the solutions of the associated quadratic equation, ax squared plus bx plus c equals 0. So when we talk about solving quadratic equations, we're really talking about finding the zeros, okay? That what we're going to do is set the equation equal to 0. Technically, we're setting the function equal to 0. This ax squared plus bx plus c equals f of x. And here we're setting f of x, or the y value, to 0, which means we're actually finding the zeros. Quadratic functions have a real number or an imaginary number zeros. Quadratic can have real number or imaginary number zeros. And quadratic equations can have real number or imaginary number solutions. This is really just saying the same thing, because the quadratic equation, by definition, is finding the zeros. Okay. So we're going to use some different principles in order to solve these equations. The first one is called the principle of zero products. And by product, we're talking about multiplication. So if a times b equals 0 is true, then we know that either a has to be equal to 0 or b has to be equal to 0, or both of them. Okay? So if we have ab equals 0, if we have any product, any multiplication equals 0, then we know one of those factors is equal to 0. And if a equals 0, or if b equals 0, if either of the factors equals 0, then the product is equal to 0. This is kind of circular logic, okay? But we're going to use this when we factor quadratics, because we factor them into a product of two binomials, and then we can set each binomial equal to 0 each. Okay? The principle of square roots says that if x squared equals k, and k being a constant, then x equals both the positive square root of k or the negative square root of k. And this is a common mistake that students make. They just look for the positive square root when they're solving an equation, a quadratic of this form. So remember, if you have x squared equals a constant, you need to consider both the positive and negative square roots. So let's look at how we solve a quadratic equation. Okay? So we have 2x squared minus x equals 3. The first thing we want to do is set this equation equal to 0. Okay? So we're going to subtract 3 from both sides, and we get 2x squared minus x minus 3 equals 0. That's the first thing we're going to do when we're trying to solve these quadratic equations. Okay? Then the next thing we're going to do is we're either going to factor this quadratic equation or we're going to use the quadratic formula. In this first case, we're just going to factor the quadratic equation. I'm not going to go through this factoring. You can do that on your own. But if I factor 2x squared minus x minus 3, I get x plus 1 and 2x minus 3. Notice this is a product. This is the quantity of x plus 1 times the quantity of 2x minus 3 equals 0. Since we factored it, what we're going to do is use the zero product property and set each factor to 0. So x plus 1, the first factor equals 0, and 2x minus 3 equals 0. And then we're going to solve each of those simpler equations. And so we get x equals negative 1 by subtracting 1 from both sides. Here, by adding 3 to both sides, we get 2x equals 3. And then dividing by 2 on both sides, we get x equals 3 halves. Okay? It's really important that you do a mental check and ask yourself, when you get these answers, do all of these answers make sense? And this is really, the mental check is more prevalent when you're doing an application problem. Most application problems are asking about some value of x that can't be negative. How many widgets should I make? What time will I arrive, etc. And so negative answers don't make a lot of sense. So you have to kind of think through that and just do a quick mental check after you solve the problem if those answers seem correct. You also should, especially in a testing environment, is to check the solutions. So here all you're going to do is go back to the original equation. Here we had x equals negative 1 and we plugged it in for every x. And we're just going to see if it indeed does equal 3 from the original function or equation. Again, we have 3 equals 3, so this is correct or true. And remember, we also had x equals 3 halves, So we plug that in for x, and we continue to solve. And again, we get 3 equals 3, and so we get another true answer. And so both of these answers are valid solutions for the quadratic equations. Let's look at another one. And this example specifically is if b equals 0. Remember, it's ax squared plus bx plus c equals 0. Well, if there's no just straight x term in the problem, we're going to use a different method for solving this, and that we're going to simply solve algebraically using the principle of square roots. So instead of, this is already set to equal to 0, we're going to solve for x squared, okay? So the first thing I'm going to do is add 10 to both sides, because I want to get, I'm going to isolate the variable x. Then I want to get x by itself, so I'm going to divide both sides by 2, right? 2x squared divided by 2, 10 divided by 2. And then I've got x squared equals 5. Here's where I'm going to use the principle of square roots. Remember that if I have x squared equals 5, then x equals the positive or negative square root of that, of 5. Okay? Again, I'm going to check this. I'm going to plug in plus or minus the square root of 5 into our original equation. Since it's squared, a negative will be positive as well, so I can do them both at the same time. And indeed, I do get 0 equals 0. So both of these are valid solutions for the quadratic. Okay, pay attention here. Well, luckily this is a video, so you can rewind and watch it again. But this is a little more involved. So I've got all the steps here. I'm going to work through this problem at the same time, showing you how to do it, and you'll see all the steps so you can rewind if you so choose and see it again. All right, so the first thing I'm going to do if I'm trying to complete the square is I'm going to isolate the terms with variables on one side and arrange them in descending order. This just says get all the x's on one side and all the constants on the other. Descending order just says put them in standard form. So notice here I've got 3x on the right and I've got 2x squared on the left. I want the 3x over with the x squared. I've got negative 1 or minus 1 on the left, and I want that on the opposite side. So I'm going to subtract 3x from both sides. So I move the 3x over, and I'm going to add 1 to both sides so that I move that over. And so when I do that, I didn't show those steps, but I think that you can follow along. We get 2x squared minus 3x equals 1. And we've completed the first step. And that's getting all the x's on one side and all the numbers on the other, which is what we do algebraically anyway. So the first step is okay. Now it gets a little bit more involved. Divide by the coefficient of the squared term if that coefficient is not 1. Well, the squared term is that first term, and the coefficient is simply the number in front, which is a 2. So we're going to divide both sides of the equation by 2. Divide both sides of the equation by the coefficient on the squared term, the multiplier on the squared term. Now, when you're dividing more complicated equations like this one, I suggest that you divide each term by the 2 so you don't cancel out by mistake. If you put 2x squared minus 3x, all of that over 2, you might think you could cancel out the 2 in front of the x squared with the 2 in the denominator, but that will not work. So when you're doing these problems, I suggest again that you just write slash or divided by 2 under each one. And that's what I'm talking about. 2x squared divided by 2 minus 3x divided by 2 equals 1 divided by 2. Now I can simplify this and I get the 2's cancel out in the first term, so I just get x squared minus 3x over 2. Notice this is really 3/2 x. So I get minus 3/2 x, and that all equals 1/2. So now we've completed the second step. All right. Get all the x's on one side, divide by the coefficient in the squared term. And what this does is it sets up that the first term will always be just simply 1x squared. And that's what we're shooting for. Okay? And it gets a little more complicated. Complete the square by taking half the coefficient of the first degree term and adding its square on both sides of the equation. Now don't panic. It's a mouthful. It's a lot to think about. But when we're talking about the first degree term, we're really talking about the b term, right? Because x to the power of 1 that's the degree. Remember, the degree is the exponent on the variable. So we're looking for the coefficient on the x term, not x squared, just the x term. Okay? So we're going to take half the coefficient and then square it. Okay? So the coefficient is 3/2. We're going to take half of it, which means multiplying it by 1/2, and we get 3/4. Then we're going to square it. 3/4 squared is 9/16. This 9/16 we're going to simply add to both sides. Okay, so we get x squared minus 3/2 x plus 9/16 equals 1/2 plus 9/16. And I went ahead and reduced that. You wouldn't have this middle part in there. 1/2 plus 9/16. 1/2 is 8/16. So 8/16 plus 9/16 is 17/16. Okay? Now, this sounds difficult, but it's really not too hard. Step 4 is to express one side, really the left side, wherever the squared term is, wherever the quadratic is, as the square of a binomial. What we have done is we've set up a perfect square. And it's very simple to find that. It's really just the square root of c. Take the square root of c. The square root of 9/16 equals 3/4. And because we have x minus the a term is minus the b term, this is going to be x minus this 3/4 squared equals the 17/16. Here's the binomial that we're setting up, the square of the binomial, and all we had to do is take the square root of c, the c that we added in, and this will set up that equation, okay? Now, if this equation up here was x squared plus 3/2 x plus 9/16, then we would have an x plus 3/4 squared here. So whatever math operation is between a and b, minus or plus, is what your binomial is going to be as well. Okay? Now we're going to use the principle of square roots, right? When we have something squared, the answer is the positive or negative square root. So x minus 3/4 equals plus or minus the square root of 17 over 16, Well, this is the square root of 17 over the square root of 16, which of course is just 4. So x minus 3/4 is equal to plus or minus the square root of 17 over 4. And then we're going to add 3/4 to both sides to solve for x. And here we get our answer. Okay? So again, we're going to isolate the terms, the x terms, the terms with variables on one side and the constants on the other. We're going to divide that equation by the coefficient on the squared term. We're going to figure out what to add to both sides by taking the coefficient on the middle term, on x, multiplying it by 1/2, and then squaring it. Once we do that, we're going to rewrite the quadratic as the square of a binomial using the square root of c inside of that binomial as our constant, x plus or minus whatever the square root of c was. That squared equals our constant on the other side. And then we're going to use the principle of square roots to solve this. So again, the plus or minus the square root of the right side, and then simplify. Another way to solve quadratic equations is by using something called the quadratic formula. The solutions of ax squared plus bx plus c equals 0, where of course a cannot equal 0, are given by x equals negative b plus or minus the square root of b squared minus 4ac all divided by 2a. This is a formula you need to know. It will not be given to you on the test. This is something you need to commit to memory. And a student helped me with a really simple story that I kind of like and most of my classes like to remember the quadratic formula. This is the quadratic formula. Are you ready for the story? It's kind of like a bedtime story. Well, maybe not. Once upon a time, there was a negative boy. He couldn't decide whether or not, plus or minus, to go to a house party. He decided to be square, and he missed out on 4 awesome chicks. And it was all over by 2 a.m. One more time. Once upon a time, there was a negative boy. He couldn't decide whether or not to go to a house party. He decided to be square, and he missed out on 4 awesome chicks, and the whole thing was over by 2 a.m. So that's an easy way to remember the quadratic formula. All we're going to do is we're going to substitute the value of a, b, and c into this formula, and this will give us our answers for the zeros of the quadratic. This formula can be used to solve any quadratic equation. Some quadratics are not possible to factor or are very difficult to factor using analytical skills. But the quadratic equation will work every single time. The quadratic formula will work every single time. So let's look at this. Find exact solutions and approximate solutions rounded to the thousands of 3x squared plus 2x equals 7. Okay? The first thing we're going to do is set the equation equal to 0, put it in standard form, and then recognize that a equals 3, it's the term in front of x squared, the coefficient in front of x squared, b equals 2, what's in front of x, and c equals negative 7, what's the constant at the end. Okay, so now we're going to plug these values into the quadratic equation, which will give us the exact solution. So we get negative 2, negative b, plus or minus b squared, 2 squared, minus 4 times a, which is 3, times c, which is negative 7, all divided by 2 times 3, 2a. Okay, so if we reduce this down, we get negative 2 plus or minus the square root of 4 plus 84, because negative and negative is positive, all divided by 6. We get negative 2 plus or minus the square root of 88. I can see a 4 will go into there, so this is the square root of 4 times the square root of 22, or negative 2 plus or minus 2 times the square root of 22 over 6. I now see that I have a common factor of 2 in the numerator and a common factor of 2 in the denominator. And I need to be very careful that I don't just try to cancel this 1 2 out with the 6. in the denominator. So I refactor the numerator and the denominator to make sure if I'm canceling things out, I'm only canceling out products. Okay, so if I factor a 2 out of the numerator, I get 2 times the quantity of -1 plus or minus the square root of 22. If I factor the denominator, I get 2 times 3. And now, since these are being multiplied, division is the opposite of multiplication, and 2 divided by 2 simply equals 1, I can, as we say, cancel them out, but it's really being replaced by 1. So my exact solutions are -1 minus the square root of 22 over 3, or -1 plus the square root of 22 over 3. When I leave it in radical form, when I have a square root that's not a perfect square root and I want the exact solutions, I have to leave the square root intact. If I want an approximate solution, then I will put this in my calculator and round. And in this case, it asked us to round to the thousands. And if I do that, I get two answers. They are -1.897 and 1.230. I strongly suggest that you pause the video right now and plug these into your calculator to make sure that you feel comfortable getting these values. A lot of times students will forget that they need to put the entire numerator in parentheses before they do division, because otherwise it's going to do -1 minus, and then it'll look like a fraction, the square root of 22 over 3, instead of this whole difference first. There's a special part of the quadratic formula called the discriminant. When you apply the quadratic formula to any quadratic equation, you will find the value of b squared minus 4ac. This is the part that's in the house, as I say. It's the radicand, or what's underneath the square root, b squared minus 4ac. And this value of what's in the house, it can be positive, it can be negative, or it can be 0. And again, just that part in the house, the radicand, is called the discriminant. Okay? For ax squared plus bx plus c equals 0, where a, b, and c are real numbers, that's just a given for a quadratic formula. If the discriminant is equal to 0, if we plug in those values and we get 0, then our answer to the quadratic equation is only going to have one real number solution. For example, x squared plus 4x plus 4 equals 0. If we solve this using the quadratic formula or using factoring, we're only going to get one answer, and that's x equals -2. We're only going to get one answer, and it's going to be a real number. And here you can see the discriminant calculated from this specific quadratic. B squared, 4 squared, minus 4 times a, which is 1, times c, which is 4. And if we do that math, we get 0. And we can see that there is only one answer there. If the discriminant is greater than 0, or if the discriminant is positive, we're going to get two answers, and they're going to be real numbers. They're going to be two different real numbers. In the case of x squared minus x minus 6 equals 0, x can be either -2 or +3. And again, if we look at the discriminant, we'll see that b squared, b is -1, minus 4 times a, which is 1, times c, which is -6, gives us a +25. Okay, so if the discriminant is positive, we have two answers. If it's 0, we have one real answer. And then our last case is if the discriminant is negative, if it's less than 0. If the discriminant is negative, we're going to have two different imaginary number solutions, or we're going to have complex conjugates. Okay, so for example, if I have x squared plus 4 equals 0, then using our square root property, we get x equals plus or minus the square root of -4. Hey, we just learned how to take the square root of a negative number using the imaginaries, and this would be plus or minus 2i. And again, if we look at the discriminant, we see there's no b term here, so b, there's no x term, so the coefficient in front of that has to be 0, because this could be written as x squared plus 0x plus 4. So if there is no x term, b is equal to 0, minus 4 times a, which is 1, times c, which is 4, and we can see that we get -16. Okay, so this is just this is a quick test to see how that your answers are right. If you only got one answer, the discriminant should be 0. If you got 2 real numbers, your discriminant should be positive. And if you got 2 imaginary numbers, then your discriminant should be negative. How will I know? You'll get an imaginary number when, of course, you're taking the square root of a negative number, which is what the discriminant is. It's the square root of the discriminant. So if it's negative, we know it's got to be an imaginary solution. Another thing we're looking at today is things that look like quadratics but aren't quadratics. Some equations can be treated as quadratic provided that we make a suitable substitution. Look at this. X to the 4th minus 5x squared plus 4 equals 0. It kind of looks like ax squared plus bx plus c, except it's not raised to the squared power. So the clue that you want to look for is notice the power on the first term, which is a 4, is double the power on the middle term, which is 2. If you have this set up where the first term's exponent is double the second one, then you have an equation that can be reduced to a quadratic. Okay, it sort of looks like a quadratic, but that's the real clue, that the first exponent is double the middle term exponent. So if we think about x to the 4th, and we know since it's double the exponent, then this is technically equal to x squared squared, because when we raise a power to a power, we multiply the exponents. So we can use a substitution of this inside thing, or the variable and the exponent in the middle term. So we set u equal to x squared and rewrite the original equation as a quadratic. So first here I just rewrote it in terms of x squared and I made them all red. So we know that x to the 4th is x squared squared. There you see the red x squared squared, minus 5 x squared, I made the x squared red, plus 4 equals 0. Well, everywhere we have an x squared, we're going to substitute in a u. So notice we get u squared minus 5u plus 4 equals 0. Well, now we do have a quadratic equation, and we can solve this using factoring, or we can use the quadratic formula. We can do whatever we want. If we do go ahead through this and solve it, and we're going to look at the whole problem in just a second, we would get that u equals 4 or 1. And this is where a lot of students stop. Be careful, it's very important. When we're solving the original equation, we want to know what x equals. And when we do this substitution, what we found is what u equals, our substitution. So we're going to have to go back and remember that whatever u equals, u equals x squared. So we have to set up 2 more equations, x squared equals 4 and x squared equals 1, because we need to solve for x. So we get 4 equals x squared, and this gives us x equals plus or minus 2. 1 equals x squared. This gives us x equals plus or minus 1 using the square root property. And any equation that's like this, that has that kind of double exponent that we talked about, these equations are said to be reducible to quadratic because we were able to reduce it to a quadratic equation and then solve it, or it's quadratic in form. Notice that this equation, this original equation, x to the 4th minus 5x squared plus 4 equals 0, actually has 4 answers. Plus or minus 2, positive 2, negative 2, positive 1, negative 1. And that's not unusual. Okay? So this is really that same equation. We're just going to go through the steps so you can see them. So I'm going to go through it pretty quickly. We substitute in u for x squared. We then factor it. We get u minus 1 and u minus 4. We set each of those factors with the 0 product property to equal to 0 and solve for them. We get u equals 1 and u equals 4. We then substitute back in u equals x squared so that we can now solve for x. And then we use the square root property that x equals plus or minus the square root of 1 or plus or minus the square root of 4. And we get plus or minus 1 or plus or minus 2. So the solutions, again, for this problem were negative 1, 1, negative 2, and 2. And here you just see it in a more concise fashion going through. I wanted to show you that problem from start to end, just with the problem. We're going to have some applications in this section too, and these are often translated to quadratic equations. For example, the time of free fall. The formula s equals 16t squared is used to approximate the distance s in feet that an object falls freely from rest in t seconds. So s is our distance and t is our time in seconds. The Petronas Towers in Kuala Lumpur, Malaysia are 1,482 feet tall. How long would it take for an object dropped from the top to reach the ground? So when we're doing these applied problems, remember I told you, think first about what you're looking for. What is the question? How long? What is long? Is it talking about the length of something? No, it's talking how long would it take. It's talking about time. So we're trying to find time in here, okay? So when we look at our formula, we have time here, and s is equal to distance, and we're given the distance, how far it falls, okay? So we're just going to simply substitute in 1,482 for s in the formula, and then solve it algebraically. We're going to divide both sides by 16, and then we're going to take the square root of t squared equals 1,482 divided by 16, so t is going to equal the square root of that. If we do that on our calculator, we get t equals 9.624. Hey, we forgot the square root property. Why don't we do plus or minus the square root when we're solving this? Well, this is that idea about the mental check. How could something take negative seconds, right? If we consider the positive and negative, we're going to get plus 9.6 or negative 9.6. And I'm not really sure, maybe that's an Einstein theory of relativity, how we could actually get to a negative 9. But that's why we don't have plus or minus in this problem, because it's an application, and we're asking how long, and time will only be positive. And then we want to be able to make sure that we can translate anything. It would take about 9.624 seconds or 9.6 seconds for an object dropped from the top of the Petronas Tower to reach the ground. Okay? That's the end of this section. I think hopefully you've got something to go on here. I know that completing the square is a challenge, as well as there's some other challenging concepts in here. But the good news is you can always go back and review. Reach out whenever you need help. And I'll see you in the next lecture.